Assalamualaikum and hi. This is part 5 video of chapter 3 gas turbine cycle. In this video, I'm going to explain the last subtopic, which is Brayton cycle with intercooler, with reheating and with regeneration. Brayton cycle with intercooling, with reheating and with regeneration. Brayton cycle with intercooling, reheating and regeneration. So this is an actual diagram of the Brayton cycle with the intercooling, reheating and regeneration, a simplified one. And this is the TS diagram, which is the actual diagram of the open cycle, which is the diagram on your left hand side. And as I already mentioned, we can increase the efficiency of the Brayton cycle by increasing the work net. And there is a two way to increase the work net. First, by decreasing the work in by the compressor. And how do we do it? We change the compressor into multi-stages compressor. The number of stages will increase the compression process, and it is an isothermal process, and the maximum stage is 3 stages, whereby if you increase more than 3, it is not economical to the overall system. And this is the TS diagram, as you can see at the bottom of your slide. And as you can see here, we can put it a number of stages. However, it is not economical to the overall process. So the best performance should be that the pressure ratio between the input and output from the compressor 1 and compressor 2 should be the same. So it can minimize the work in by the compressor. So the function of the intercooler is to decrease the average specific volume, and it also will increase our lowering the temperature of the fluid leaving the intercooler. So as you can see in the TS diagram on your right hand side, top of your right hand side, TS diagram here. So in the stage 1, which is air inlet into the compressor 1, and the outlet of it, the pressure, the temperature is a bit higher. So since we, after the exit of the compressor 1, the air goes into the intercooler. So the intercooler will reduce the temperature of the air into temperature at state 3, and then it goes back into the compressor. So this is the function of the intercooler. Another way of increasing the work net is by increasing the work out or the work by the turbine. So the same with the turbine, we put the multi stages where the number of stages will increase the expansion process, and it's an isothermal process. And the maximum stages with the economical is the best number of stages is 3 stages, and for the best performance, the pressure ratio from the first compressor, first turbine and second turbine should be equal. Same with the compressor. And the function of reheating is to increase the average specific volume, and it also will increase the temperature of the air that goes into the reheating process. So change the temperature, it increase the temperature difference here, and also increase the regeneration potential. Although from this how to say explanation, you find that with the intercooling and reheating, it shows that it looks like the efficiency of the system, overall efficiency of the system will increase. However, in the actual cases, the intercooler and reheating will decrease the efficiency of the system. However, with the regeneration, we should include the regeneration to include all this. So the efficiency of the system will be increased because of the regenerations. Brayton cycle with intercooling, reheating, regeneration, specific volume change. Okay, I already explained in the previous slide about the specific volume change from the work compressor and also turbine. So here I'm going to explain the scenario behind it. So work in and work compressor, intercooling, average specific volume. will decrease. So this is the compressor 1 and compressor 2. From state 1 goes into compressor 1, and the output of it is stage 2, and then it goes into compressor 2. The output of it is stage 4. Okay, so let's assume that the specific volume that goes into the compressor 1 is 80 meter cube per kg, and the output of it is 60 meter cube per kg. And the work in from this process, compression process, is 100 kilojoule, and it goes back into the compressor state 3 because there is no reheating, intercooling, so the specific volume is still 60 meter cube per kg, and the output of it is 40 meter cube per kg. So there is another work in, which is 100 kilojoule to the compressor 2. And as you can see from the graph, which no intercooler and the energy consumption applied to the compressor, we have 100 kilojoule, and the meter cube, which is the specific volume, is 80, 60, 60, and also 40 meter cube. However, let's say if you look into another case where compressor 1 and compressor 2 with the intercooler, let's say the specific volume goes into the compressor 1 is 80 meter cube, and it goes out of the compressor 1 is 60 meter cube. And since and the work applied is 100 kilojoule, and since it has intercooler, the specific volume will be changes from 60 to 50 meter cube, and the output of it is 40 meter cube, and the energy needed to compress the compressor 2 is 50 kilojoule, which is less than the energy needed in the process without the intercooling. So in this case, you can see that we have the reduction in the specific volume, and also reduction in the energy consumptions. Brayton cycle with intercooling, reheating, regeneration, specific volume. Now we look into the work at the turbine, work out by the turbine. So as you can see, the reheating process increase the average specific volume, the average, as you can see here. The air from state 6 goes into the turbine, state 7, from 100 meter cube per kg specific volume, and goes out of the turbine at the equal to the specific volume. The output of it is 220 meter cube per kg, and the work generated is 300 kilojoule, and then goes back into the turbine 2 with the specific volume go to 120 meter cube per kg, and goes out to the state 9, and the specific volume is 140 meter cube per kg, and the work out is the 300 kilojoule. And this is the analysis from it. As you can see, in the V6, which is the specific volume at the state 6, at the state 6 is the 100 meter cube per kg, and state 7 and state 8 is 120 meter cube per kg, and the energy needed, energy produced by this turbine is 300 kilojoule for both process, turbine 1 and turbine 2. However, let's say we include the reheating process. Let's say the V, which is the specific volume at state 6, is 100 meter cube per kg, and the output is 120 meter cube per kg, and the work generated by the turbine is 300 kilojoule. And then due to the process reheating from state 7 to state 8, the specific volume increased to 135 meter cube per kg, and the output of the at the state 9 is 140 meter cube per kg, same with the process without the reheating. And the work out from the turbine is 450 kilojoule. And let's say we look into the energy analysis. The specific volume is increasing from V7 to the V8, and the energy also will have a large increment from turbine 1 and also turbine 2. A Brayton cycle with intercooling, reheating, regeneration, and temperature change. Now we look into the cases of the temperature change. We look first into the work by the compressor. So this is the cases of the compressor without the intercooling. As you can see, the temperature at state 1 is 50 degrees Celsius, and the output of compressor 1 is 25 degrees Celsius, and the input of compressor 2 is 25 degrees Celsius, and the output of it is 35 degrees Celsius. And from the temperature, we can see that the temperature keep on increasing from state 1 to state 2 and state 3 with the same temperature, and state 4 the temperature is extremely high compared to temperature 1. Now we look into the compressor with the intercooling. So temperature at state 1 is 50 degrees Celsius, and the output of it 25 degrees Celsius. And due to the intercooler, the temperature at state 2 is decreased into 20 degrees Celsius, and the output of it is 30 degrees Celsius at state 4. So from this, you can see it lowering the temperature at the state 4 from 35 turn out to be 30 degrees Celsius. Okay. Brayton cycle with intercooling, with reheating, and with regeneration due to the temperature change. Okay, now we look into the temperature change of the turbine. This is one cases of the two stages of turbine without the regeneration. And as you can see, the temperature at state 1, at state 6 is 500 degrees Celsius, and state 7 and 8 is 450 degrees Celsius, and at state 9 is 400 degrees Celsius. So as you can see here, the temperature is decreasing from 500 degrees Celsius goes into 450 degrees Celsius, and then the output at state 9 is 400 degrees Celsius without reheating. So the temperature is lower. However, if we have the reheating process, the temperature stays still, let's say at 500 degrees Celsius, and state 7 is 400 degrees Celsius, and state 8 the temperature will be 550 degrees Celsius, and the output at state 9 is 500 degrees Celsius, which is larger than the cases without the reheating process. So in this case, you can see the analysis of the temperature. So we have the temperature increasing at the temperature at the state 7 and state 8, and the average temperature at state 9 is equal to the temperature at the state 6. So this is the analysis of the reason the higher temperature, as already explained in the previous slide. Okay, this is the list of the question from the Chengel books. So you can try to answer most of this question. Maybe some of the question will be used as your final question. This is the end of part 5 for chapter 3, and which is the last subchapter of chapter 3. And for your attendance, just write my name as the answer. Hopefully you enjoy this video, and thank you.